Okay, good afternoon, good evening, maybe good morning, depending on where you are from. Today is July 2nd, 2020, and it is 3 p.m. Eastern Daylight Time. And I would like to thank Juha Vierinen for coming to present to us today. Juha is an associate professor of space physics in the Department of Physics and Technology at the University of Tromsø in Norway, and he's also a ham radio operator. And one of the reason we have asked him to speak today is that he has written code for listening to passive ionosons and also for doing his own sounding that runs on the EDIS USRP N200 and N210 software-defined radios. And these are research-grade radios, and they are very similar to what we are trying to design and build with the Tangerine SDR and the Personal Space Weather Station. And so our hope is that he'll be able to tell us about what he has designed, and he has been kind enough to release it as under open source licenses. And then we're hoping to be able to implement some of this technology into the Personal Space Weather Station. So with that, I would like to hand it over to Juha, who I will unmute, or you can unmute yourself. And thank you very much, Juha.
All right, thank you. So I guess I need to share my screen somehow. Okay, so can everyone see my screen?
Yes, you're making me want to make a trip.
So you can see some snow and some skiing, right?
Yep. I'm ready.
Yeah. Well, anyone's welcome to come ski. If somebody wants to ski, they're my friends, and they're always invited here. Actually, we can still ski here. I was skiing on midsummer. There's still snow on the mountains. This was a very nice year. Okay, so I need to minimize that. Okay, and you can still see, I guess you can see the slides now, right? Can you see the slides? Yeah, good. Okay, well, hello everyone. It's a great pleasure to talk to the HamSCI community. I've been following the HamSCI activity kind of maybe a little bit as an outsider, evolving over the last few years or more than that. And there's definitely a lot of really interesting activity, and especially this Tangerine SDR and this Personal Space Weather Station is really exciting, and I'm definitely going to acquire a few of those once they come available. And hopefully I can contribute somehow to this project, and perhaps these HF ionospheric sounding open source projects that I've been developing might be one way to get involved. And I'd like to thank Nate and Dev Jossi for inviting me here. All right, today I'm going to talk about 3 different open source software projects that I've been involved with or led over the past 10 years. One is the GNU Chirp Sounder, which is an open source software that allows you to make oblique ionograms using these FMCW transmitters that you can see on HF. Then I'm going to talk about some more recent work that came out of the IARPA PINS challenge, the Passive Ionospheric Non-Characterized Sounding Challenge. That was last summer. I participated in that competition, and the software that I developed for that competition, I'm in the process of releasing as open source. And this software might be useful also for the Personal Space Weather Station. And finally, I'd like to talk about a new software-defined radio-based ionoson that I'm developing. This is an ionoson which is purely written in Python. It's only a couple hundred lines long, actually. And we just finished a master's project on this. And so there's a master's thesis available online. I have a link to that thesis if anyone is interested in reading about that. And this is, again, something that we might want the Personal Space Weather Station to do. Okay, So first, the GNU Chirp sounder. Some of you might have even tried this out. I know that a few of you have used this. I think I probably developed this sometime around 2010, and I haven't really done much to update it. You know, every few years I will make sure that the code runs and compiles on the latest version of GNU Radio. What is this piece of software? It's a custom GNU Radio block, signal processing block that just does the FMCW down conversion. So it de-chirps the chirp signal and then does a dynamic spectrum to get the inogram. This software relies on GPS for timing because you need to know when the chirp starts, when the FMCW signal starts. And the FMCW signal is a linear frequency sweep, by the way. It's got some bells and whistles, and you know it has for example, a pre-whitening filter to reduce radio station interference. So it allows you to block out the radio stations and only see the chirp signal. The software only supports the USRP N200 series of hardware. It also supports the older generation USRP2, but they're essentially the same device. And this is what it looks like. I mean, it's pretty much what you know, a subset of the functionality of Tangerine SDR. It's got an FPGA which does digital down conversion and up conversion. It's got you know, a port for an external pulse per second and a 10 megahertz, and it's got one slot for a transmit board and one slot for a receive board. And this one is a basic RX, which is essentially an SMA connector and a one-to-one transformer, which is fed directly to the ADC. And it's got an Ethernet, 1 gigabit Ethernet output. But and optionally you can put a GPS DO onto this one. I don't have one mounted, but I typically use the onboard GPS DOs. I believe the GPS DO is developed by Jackson Labs. It's a small one. I really like these radios because they're simple, reliable, and they just work. And you can get timed samples and take those timed samples and feed them to your Python signal processing software and do whatever you want. The chirp sounder originally was intended to act as a vertical sounding inogram receiver for the Sodagulla Geophysical Observatory, where I was working at that time. But it has since been used for oblique sounding together with the US over the horizon radars and the Cyprus over the horizon radar as well. The code is available now. Because I'm not working at the observatory anymore. I've shifted the code now to GitHub, so you can get access to the code if you go to this URL. Okay, so what is the typical signal that you can observe with the GNU Chirp sounder? The relocatable over the horizon radars that are on the US continent and in the Caribbean, these are signals that you will typically see all the time. If you do a dynamic spectrum on your radio, you will see these sweeping chirps. These are most likely caused by these over the horizon radars, which are used to look at intercontinental ballistic missiles and drug runners coming from South America. Here are the locations of some of the systems that I know of. There's one in Chesapeake Bay, there's one in Texas, and there's one in Vieques in Puerto Rico. I think there are new ones as well. This figure is from Wikipedia, and it looks like they actually don't have the location of Puerto Rico correct. All right, well, everyone knows where Puerto Rico is, right? Okay, and this is what a dynamic spectrum looks like when one of these chirp sounders is on the air. This is a screen grab that I got from Alexandru Sesete. If you zoom in, you can see this diagonal chirp. That's a chirp sounder. That's one of these over the horizon radars performing a channel sounding, sending out a sweep from, depending on the mode, sometimes from 2 megahertz to 20 megahertz, sometimes from 8 megahertz to 40 or 50 megahertz even. But if you then take this signal and process it, you can make an inogram. Here's an example of the software, of the hardware that you can use. This is a dual channel version of the Chirp sounder. It's just an active broadband antenna and fed into a USRP. I should have maybe added a low pass filter here. And these USRPs are then synchronized to a GPS. I've used external but also internal GPS receivers. And then you just connect this USRP to a computer where you have the software doing its thing. One piece of software for doing the chirp down conversion, and then one piece of software for analyzing the inograms. Here's an example of the antenna. If you want to get circular polarization, what you want to do is you want to have two linearly polarized antennas orthogonal to one another, and you can get the ordinary and extraordinary mode of propagation in the ionosphere. Here's an example of an oblique ionogram that you can make. This one was recorded in 2013 when I was at MIT Haystack Observatory. And I believe this transmitter was, in Puerto Rico. And this is with the widening filter turned on. So all of the radio stations are notched out. They're not completely removed, but to a large extent they are, and you can only see the ionogram. Okay, and you can see the, this ionogram mostly shows F region echoes. You can see the O mode trace and the X mode trace. And from this you can determine, if you know the geometry, you can pretty much determine what is the F region peak electron density. And if you do a little bit more work, maybe a lot more work, you can estimate the electron density profile on the bottom side of the ionosphere. Here's another example of what the software can do. This is a vertical ionogram with the Sodankylä Observatory ionosonde. That ionosonde is an FMCW transmitter, which is a linear frequency sweep, 500 kilohertz per second. This is using the dual polarization receiver, where I focused on the ordinary mode, the O mode, which is unaffected by the electron gyro motion in the magnetic field. And you can see the F region as well as the E region echo, or the E region trace. And you can also see multi-hop echoes. These echoes are caused by the radio wave bouncing back and forth between the Earth and the ionosphere. And at the zero range, that's where you have the transmitter. The transmitter is about 1 kilometer from the receiver. So you can use this software also for a vertical ionosonde where the transmitter and receiver are nearly co-located. And the units here on the color scale are power in dB. So you can see that with HF, you often, especially with these ionospheric soundings, you often end up with dynamic range, which is approaching 100 dB, or sometimes even more. But of course, this is after the processing. So I don't need 100 dB from the analog to digital converter. I only need 100 dB after the signal processing has been done. So it's 14. This was using a 14-bit ADC. With dual polarization, you can measure the and two linearly polarized orthogonal antennas. You can measure the phase difference between these two antennas. And if you have an ordinary mode, you will have a plus 90 degree phase difference between the linear polarizations, and with the extraordinary mode, which is the orthogonal circular polarization, you will see minus 90 degree phase shift. So you can also do more complicated things like look at polarization of the echo, or polarization of the reflected signal. Okay, any questions about the chirp sounder before I move on to the next topic?
I have a quick one here from VT. Hi everybody, this is Zach from VT. Did you need to use the MIMO synchronization cable for the pair of USRPs? And that's kind of a follow-on to that. Did you have any weird issues with UHD and the phase tracking when it came to the polarization discrimination? I've heard of some kind of weird phase issue with UHD where it starts up with like a random phase offset. And did that affect anything when you were trying to do the polarization discrimination?
Okay. First of all, I did not use the MIMO cable because I wanted to maximize the bandwidth, and I wanted to get, if I want to get 25 megahertz of bandwidth, I need to transfer 100 megabytes per second over the Ethernet, which is pretty much the maximum bandwidth for 1 gigabit Ethernet. So I actually have separate cables for both USRPs. I've also done, 8-channel, 16-channel versions where I have a separate cable from each USRP, and I'm using a fan-out buffer to split the pulse per second signals. Edis Research has a fan-out buffer, which is quite nice. There's even one which has a GPS DO built into it. I've used that with very, very good success. I haven't had any issues with the phase randomizing. I've even done a characterization of the stability of the phase, and it's pretty good. Even if you power down the devices and power them back up, they'll have a very similar phase or time delay between one another. Measured in tens or definitely less than 100 picoseconds.
How powerful a PC are you using?
Depends on the how many channels I want to process. For a dual channel receiver, and one sounding, if I just want to do one sounding at a time, I can just use a standard PC. Dual core, quad core is fine. The Chirp down conversion takes about 20% of the CPU for a modern Intel Core i7 CPU. But if I want to process multiple anagrams simultaneously, then you need more cores.
Yes.
Juha.
Yes.
Yeah. How do you choose if you want to do only one sounding or multiple soundings?
There's a configuration option, which is it's a list of sounding parameters. It's a list of lists. So each list is running on a separate parallel thread.
That's in the code, like in the software that you have written.
Yeah. Let me see if I can.
Yeah, it will be nice if you. Yeah, it will be helpful if you can initiate where, like I've just started looking at the software and I'm trying to see if I can get any output, and if you can show an instance of running your software and getting an output, that will be helpful.
Juha, this is John from HamSCI.
Yeah.
So a couple of things. One, the code would work with any sort of Edis USRP, correct? As long as you have the right.
There's only one Edis USRP which is nice for HF, and that's the N200. Maybe the X, and if you put a basic RX on it, but that's overkill because you don't need that bandwidth.
No, we know it's the X300 has been the only thing they've been willing to put those basic RX, and I've been bugging them to do that. But another thing, could this be augmented to have a digital RF output so you could save the data to disk right away?
It could be,
and then,
but the raw voltage is 100 megabytes per second.
True. Again, in my mind, it's just sort of like I don't know where we are. We just sort of have a huge amount of things, but that's something that could be done later. Like it could be a option that you turn on.
Yeah, for sure. I mean,
I'd be willing to help out with that too.
That we do at HamSCI, where we have a RAM disk for the 100 meg or for the 25 megahertz bandwidth channel.
Yeah.
So
This is Todd.
That was Dev Jossi, right? You were asking that question about.
Yes.
Yeah. So I believe the right configuration here is like if you want another parallel thread, you would just add another list here. You would have 5-minute repetition and start time. I don't know, 0. I don't know what the start time is now for the US ones, but 100 kilohertz per second chirp rate, and I think they have 5-minute soundings and
I had just opened this file, and I was curious if the definition that you have provided here is, does that define a specific sounder?
that defines the Sodankula sounder.
Okay. Okay.
You might not hear that in the US. It's pretty it's only a few watts, and it's a fast chirp rate, so it has low chirp rate and high resolution.
Let me rephrase my question. So if I'm just starting,
Yeah.
how do I know which transmitter will I be able to receive?
I'll answer that later. I have another piece of software which might help you with that.
Okay.
Alternatively, you can call a friend in the Navy and ask them. Paul Bernard is usually a very good source of information on what the sounding rates. I mean, when he uses this, he'll call somebody. When we were on Arecibo, when we had our Arecibo campaign, he would ask what is the timing, and then he used that timing. So,
Okay.
but they're over the air, so you can determine that. You can just listen to the signals. There's really nothing classified about it, because you can figure out the timing by just listening to HF signals. I'll get to that later.
And
Okay.
and just to complete my question, so let us suppose I have a station name, every information that is required here. If I do get that name, and when I run the code, perhaps, okay, I forgot the name, chop calculate pi.
Yeah.
Yeah, that's what I was trying to run. Yeah, chop underscore calc. So is there any way, like, what's the procedure to save the data? Like, do data come in files? Like, where is that in the code?
Well, there's a
How
program.
does the data look like, and how it is managed to be saved?
So there's this program called Chirp, which is.
I apologize because I have not completed going through it. I have gone through 2 of those, and those are my 2 initial questions. Okay, I am through the questions. Okay, so I apologize if I should be able to find the answers of the questions by myself, which I am trying to. But since I have an opportunity to request some information, it will help me to get initiated.
Yeah. So no problem. I mean, this chirp.py, this is a program that will record the sounders. It'll do the de-chirping, and then it'll save a low bandwidth signal into a file for each sounding. So once you have removed the chirp by multiplying with a negative chirp, you get a baseband signal. You get a signal which is about 40 kilohertz, sometimes even less than that. That is saved into a file. And the location of that file is defined in the config. Oh, it's defined here, -O. So you give it a directory where you want to save those files. This is the program that does the de-chirping and saves the baseband signals into the narrowband baseband signals that are de-chirped into a file, which is still complex raw voltage. And then this chirp calc, this is the one which goes through these files. It goes through these files and calculates the ionograms. And there are some command line options to do it.
To save the ionograms.
Yeah.
Okay. Yeah. So I start with the chop.py, and then after which, like, it will create files, and then I'll come to chop underscore calc pi.
Yeah.
Okay. So that's something good to know.
Yeah, and there's and there's a configuration file. There are basically 3 files. It should be a pretty simple program. All the chirp down conversion, that requires a lot of crunch power. So that is done using the GNU radio block, which is located in lib. So if you go into lib, you can find this Chirp down convert implementation, and then you can see the C++ code for that does the Chirp down conversion. That's you probably don't want to look at this unless you want to replicate this somewhere else. I needed to implement this using C++ because just to get it to be fast enough.
Juha, this is Tom. I wonder if I can ask a quick question. The pre-whitening, is that done before dechirping or is that done after dechirping?
Before dechirping.
Before dechirping, okay.
Yeah. That's also something that requires a lot of extra CPU power, so that's an option that can be disabled, I believe, in the configuration file. Yeah, widen. If you set this to true, it'll do the pre-widening, and there's some parameters here. This is the FFT length, because I need to estimate a filter using the signals on the air, right? I need to see what does the HF band look like at any given moment, and I'm by default using 8,192 point FFT to estimate that, and I'm averaging together 30,000 spectra to create the bandpass for the filter, or the inverse of the bandpass for the filter. So I basically estimate the spectrum and then I invert that to create the filter.
Okay, so you're just doing spectral subtraction?
Yes, yes. It's in the whiten implementation. So I estimate the spectrum, and looks like I'm not using any windowing anymore.
Okay, I think that's sufficient information that we can go through your code and take a look at it. That's helpful.
Yeah, here, this is where I implement the filter. So it's just 1 over square root of power on each frequency bin.
And does that get updated frequently, infrequently, slowly?
Every 30,000. I mean, that's a configurable option, but by default, it's every 30,000, 8,000 point window. So that's, let me calculate that.
That's sufficient. So we just do it once every FFT, you update it?
No, once every 30,000 FFTs. So
okay.
Every 10 times per second.
Okay.
But that can be configured. I mean, you can adjust this with these two parameters here.
Okay.
You can also adjust. You can have more frequency resolution. You can have a lower update time, or a faster update time.
Yeah. Very good. Extremely helpful information. Thank you.
Okay, more questions? I mean, you guys are pretty technically savvy, I'd say. These are pretty accurate questions. I'm impressed. This is definitely the right audience to talk about this this piece of code. Yeah, and if anyone has any updates or improvements, feel free to send them to me, and I'll add you to the author list and merge them into the code. I mean, it's.
And I should also feel free to send you more questions if I have any, right?
Sure, anytime.
Yeah.
Yeah, and this code, while it supports the N200, it shouldn't be that much of work to convert this to work on any other, like Tangerine SDR. I think it should be pretty feasible. I don't think even GNU Radio is that mandatory. I think actually,
Can you go back to your block diagram?
GNU Radio would be actually beneficial for this.
Can you go back to your block diagram for a second?
Okay.
please?
This one or yeah, this one, right?
That one, right. So what are you actually sending out over the gigabit Ethernet? Are you sending IQ data packets?
Yeah, 25 megahertz IQ,
Okay.
16-bit integer, interleaved.
Because what I was looking at is what we might do in the FPGA to reduce that bandwidth.
Yeah, Scotty, I think what possibilities are we could whiten the spectrum in the FPGA and then de-chirp in the FPGA, and then the resultant baseband is much, much, much lower data rate.
Lower data rate, yeah.
Yeah. Yeah, then you're talking about 10 kilohertz, 40 kilohertz. I mean, really, really low data rate. You do want to have more dynamic range then. You probably want to send them as single precision floating points or something.
So you mean
Or 32-bit integers.
you could do more channels then
Yeah.
and not overload your i7.
Yeah. Yeah, the algorithm for FMCW de-chirping is not very complicated. It's something that you could probably do on an FPGA. The more complicated part, I think, is going to be the whitening, because there you need to have an FFT implementation and averaging, but that's not black magic either. I mean, people do that all the time. I just don't know how to do it.
Well, we'll figure it out together.
Yeah. Yeah. All of this I did on software because I'm trying to act like a space physicist. So I have to give lectures and stuff. So it's really easy for me to just write some Python scripts, and if I really need to, I can write some C or CUDA code. That is a very low development effort for me. FPGA programming, I've done a few things, but it would be more than a full-time job if I started doing that.
I just remember one of our radio guys, a software guy, he says, it's a software-defined radio, so just give me all the data. I'll do it software.
Yeah.
He wants less processing in the FPGA, but I think I'd like to do a little bit more using the high-speed capability of the FPGA, and then maybe do some more creative things in the PC because you free up some bandwidth there.
Someone who says that doesn't understand how many gigabytes per second that entails.
Yeah.
But
How about the other applications? This is all really interesting, but I think we're getting into the nitty gritty here.
Yeah. Okay. So let me go on to the next one. This is kind of related to the first one. So this is software that came out of the IARPA Passive Ionospheric Non-Characterized Sounding Challenge competition. It was a really cool challenge because IARPA opened this challenge and they had prize money for something that I had already done. So I thought, let me participate here. But it was a little bit more complicated than that. The task was to find ionoson signals in very, very noisy data, very RFI corrupted data. You had to find them on the air. You had to detect what is the chirp rate, what is the sounding mode. You also had to detect if it's a digisond with complementary codes. You had to detect the IPP, and you had to detect all of those things, and then you had to analyze the ionogram after that. So this is basically doing ionograms without GPS DO or without having a locked clock. So yeah, I did that. So what I wanted to do after the competition, because I worked hard to do all that stuff, I wanted to release that as open source so anyone could benefit from that. And I've slowly started to develop some source code for, which I'm calling Chirp Sounder 2. But I'll hopefully add also the digisond detection and analysis later on. But this already the current version of the code, it's very rudimentary, it's very harsh. It can be used to detect chirps. So you can plug it into an antenna in a USRP and let it run, and it'll listen into all of the FMTW sounders out there, and it'll detect them. It'll figure out what their timings are and what their chirp rates are. And it'll give you a list of sounders. And this is maybe an answer to Dev Jossi's question. This piece of code will tell you when the US Navy is transmitting, when the Russian military is transmitting. It'll tell you when the Zodiac Liaison is transmitting. It'll tell you that information without having to know it beforehand. Most of the Liaisons are on regular schedules, so if you just figure them out once, then you have the numbers, you have the timing information, then you can then just run the chirp sounder. Or you can keep running the chirp detector and just detect chirp sounders from around the world and see, you know, sometimes you don't, I mean, sometimes you hear Australia and sometimes you don't hear Australia. That might be also, or the detection statistics is useful ionospheric information. Okay, I'm not the first one to do this. There's a bloke called Andrew Senior who wrote a program called Chirp View. Some of you might have actually run this program. This allows you to just plug the audio output of your ham radio gear into a sound card and detect, you know, narrowband chirps. So 10-ish kilohertz, 20-ish kilohertz chirps. I'm doing exactly the same, but I'm doing this with 25 megahertz of bandwidth. So it's essentially a wideband version of Andrew Senior's Chirp View. Okay, that's the webpage for the challenge. I hope IARPA comes up with more of these challenges. Maybe we can make a HamSCI challenge. This was really a fun competition. Okay, here's the architecture for that this piece of code. Again, I have a widening filter to not notch out the broadcast signals, but to make sure that they don't dominate, that they have equal weight to every single other spectral component. After the widening, I do a match filter. I match filter, if it's a chirp, I do a chirp match filter, which is basically a D-chirp. If it's a digisond, I do a match filter for a complementary code series with different IPPs. So I basically do a match filter bank for all the possible ionoson transmit waveforms that exist or that I have CPU power to do. And then out from that detection block comes out ionogram or ionoson sounding parameters, which is theta ml. And those ionogram sounding parameters then allow me to deterministically take the raw voltage from the ring buffer and calculate ionograms, oblique ionograms, vertical ionograms. And then the last part is that it's fed into an ionogram scaler. So I used a template matching strategy to scale the ionograms. It's a kind of a simplified version of machine learning where we didn't have a lot of data in the competition. So I couldn't train a neural network, but I kind of just made a bank of templates that would match ionograms, and that way I got the height of the F region, the junction frequency, and the height of the E region, FOF2, and the frequency of the peak frequency of the E region trace. So those came out pretty nicely. This is still work in progress. I think if I wanted to do this better, I would train a neural network to identify all of the features in the ionogram. But for that, I would need a much larger data set. But if we have a big group of hams running this kind of software, we can build up a big database of ionograms that we could then teach the computer to scale. Okay, here's the output of the detector. So on this plot, on the x-axis you have frequency, and on the y-axis you have time in units of days. Days since I started the program. And this one is about 10 days. No, it's not 10 days, 1E1. No, this one is just actually 0.07 days. So this is not many days at all. This is just maybe an hour. And this showed, in this case, I have detected 5 different FMCW sounders. So I've detected 500 kilohertz per second, 100 kilohertz per second, 125 kilohertz per second, 500 kilohertz per second, and 550 kilohertz per second FMCW signals. So it's these signals that you see on your waterfall spectrum when you plug in your IF to a software-defined radio device. The chirp rate is how fast this frequency sweep, how fast, what is the slope of this diagonal line? That's the chirp rate. So different sounders have different chirp rates. The 50 kilohertz one, I don't know where that is even. I mean, but I know that the US relocatable over the horizon radars, they use 100 kilohertz per second for their channel sounding modes. And they start at 8 megahertz typically. The 125 kilohertz per second is used by the Australian Jindalee over the horizon radar network. 500 kilohertz per second, that's the Sodankula Einezond. And 550, I have no idea who's operating at 550. I just found it by trying out different chirp rates. So what comes out of this match filter bank is it tells you like, okay, at this time and this frequency, I detected a chirp. And when you combine this information, you will be able to figure out when chirps were transmitted. And you can then feed this information into your ionogram calculation software. So, and this measurement was made in Norway, northern Norway. So even in northern Norway, quite a lot of the time we can observe signals from Australia, signals from the US, signals from Finland, which is not that far away. That's why the peak frequency is so low. And then signals from an unknown location that's transmitting 550 kilohertz per second. I don't know who that is. If anyone knows, please let me know. Also, if anyone knows who's doing the 50 kilohertz per second, please let me know. Again, if we had a network of these devices that were GPS locked, we could figure out, we could just look at the time delays and say, and triangulate where these transmitters are. And then then the data becomes much more valuable for ionospheric research. If I zoom in, it's more apparent that these are all chirps. Sometimes you see the chirps, sometimes you don't. This depends on the channel propagation characteristics. I mean, Australia is not doing very good between 8 and 10 megahertz at this time of day, but then 6 to 8 is pretty good propagation, and 10 to 20 is good propagation. Whereas the US is propagating only above 8 megahertz. And the Sodankula Einezond, which is almost a vertical sounding, is propagating only below about 5 megahertz. And these vertical lines here, sometimes you can see codars, or also over the horizon radars that are sticking to a single frequency. They also use chirps, and this chirp detector will also find chirps that stick it with one single frequency. So occasionally you can see these chirps. They are coastal, they're codars or over the horizon radars. Here's 1, 2, 3, 4, 5, about 6 days of chirps detected. So you can see the daily variation of the radio propagation because of variable ionospheric conditions. And here's an example of an ionogram that my solution for the pinch challenge could produce together with the automatic scaling. This is something that I haven't uploaded yet to GitHub, but if there's enough interest, and if maybe somebody agrees to help me out, make it more professional software, I could be convinced to release this software. But I do have a wish for this software to be open source. Okay, so before I move to the last topic, any questions about this part? Or is everyone asleep already?
I don't think so.
Yeah, the questions dropped off
Hardly.
because everyone's so focused on implementation.
People are,
I think that this is going to be, I think this could be a very valuable tool, especially for a network of these personal space weather stations, because if we're trying to use these passive techniques to find these ionosonds, having some way of automatically detecting them and locating them, it seems really important.
I'm trying to envision how you expand this out into the next dimension to show spatial reception when you have an array of these.
Well, we need to put a 3-dimensional display on it.
Yeah.
Yeah, I don't know.
Yeah.
I've seen Ethan Miller and Nate. They've come up with clever ways to visualize the whisper links. Maybe something like that. I mean, I don't know.
I mean, the first thing is just being able to properly identify where the transmitter actually is, right? Because some of these we know where the transmitter is, and some of them we don't necessarily know where the transmitter is, right?
Right.
Yeah.
And as Juha says, that's exactly why we want to have as many of these GPS locked as we can, because then we can triangulate.
Yeah, and that's going to be very important because, you know, one of the weaknesses that I've, you know, when other scientists try to poke holes in these ideas, one of the things they say is, or even like Terry Bullitt was saying, you know, if you don't know where the transmitter is, it's much harder to do actual science with it. And something like this, if we can figure out how to properly implement this across a network of these things where they go spend a certain amount of time detecting and identifying, then that information goes back to the central control system that Bill Engelke and his team is working on. And then that information can be redistributed to the other systems in the network, the other personal space weather stations. So they go from a detection mode to an actual, you know, sounding mode based on that information. I think that could be very powerful.
Has anybody in the HamSCI group started looking at the specific geolocation algorithms that would be used for this and be executed once all that data is sort of aggregated at the central processor?
I think I am trying. I don't know if I'm trying to implement these algorithms.
Okay, very cool. I'm also interested in digging into that, and maybe as a reference, there's the ADSB network from FlightAware. They do a time difference of arrival process that's all written in Python and all posted publicly. So it's a great way to get a jump start for at least time difference of arrival type stuff. So they also do a neat trick where they're using RTL SDRs that do not have GPS disciplined oscillators, but what they do is use the known position messages to calibrate out and get the timing residuals between any given pair. And then once they've calculated the timing residuals between a pair, then they can look for the messages that don't have the GPS information in the content of the message. So some tricks like that could also be brought to bear on this even for stations that are not necessarily GPS locked.
This is the way that
QESDR folks are doing HF geolocation with TDOA, and that code is available.
Who is doing?
QESDR.
Oh, Kiwi, yeah.
And because the issue is not just the time, the issue is what is the model of the ionosphere.
Right.
Because depending upon the ionosphere, it takes different amount of time to go through it. So it's not a line of sight algorithm.
But then at the same time, if you already knew where the transmitters were, and then you had GPS phase locked, then you might be able to back out the ionosphere from that.
Correct.
There's some information already in the shape of an oblique ionogram about the distance. I mean, for example, on this ionogram, how fast this frequency of the multi-hops goes down, that tells you approximately how far away it is. And it kind of approaches the limiting frequency is going to be the vertical FOF2. So that tells you something. It's not very accurate, but it gives you some idea. Other things that might help you is that often these are GPS locked. These transmitters are GPS locked, and they will be at some even second. They will start at an even second. So
I guess if even if we're not directly locked, I wonder if ranging can be done hyperbolically, like Loran C has done.
yeah,
That
something like
works on very low frequencies.
you do
Doesn't work
also
on HF so well.
yeah, you do also have to factor in the ray, the ray bending and the group velocity, which can be significantly less than the speed of light in vacuum, and that's the complicated part. I think that will never be fully resolved, but I'm pretty sure we can do something useful. And I've never heard about this Kiwi SDR. I'm going to look into that. I mean, if somebody can post a link to the chat, maybe, where I can find more information about that, that would be great.
Oh, the Kiwi SDR is great. They have a online network of software-defined radios, HF software-defined radios that you can just log into. Here's the links in the chat.
Okay.
Even if you can only get the scheduling and location for a handful of ion zones, you're talking about a huge amount of data that we don't currently have, right? Especially how many of these receivers are you planning to put out?
Us? Well, this is a citizen science project, so right now it's pretty much however many people we can get to adopt it. But but there certainly would be opportunity for putting a proposal together to do a more organized sort of deployment. So, but right now it's basically we're just developing it, and we're trying to get buy-in from the community, the ham radio community, to do an ad hoc sort of deployment.
Well, because you're effectively talking about expanding, if you have, say, even just 30 of these distributed across the U.S. and maybe only 4 or 5 ion zones that you have some sort of agreement with to figure out the location and timing of. Mm-hmm. Even say you can't figure out or you can't geolocate yourself. You're talking about effectively, hundreds of ionograms versus what we currently get in the U.S., which is 5. Right? So
yeah.
It's a huge wealth of data that's incredibly valuable to data assimilation people that doesn't necessarily have to be inverted into a profile. These oblique ionograms on their own are explicitly helpful for data assimilation if you handle them in the correct way.
And that's very important to know, because again, some people have said, there's not much information in these. And so I agree with you. I think if we do things right, or if people do things right, they can be very, very valuable.
Yeah.
One little quick thing that I might offer is just the note where you showed the on one of these slides you showed kind of the propagation sorry, right there, the multicolored ones where you're detecting like the 50, the 100, the different chirp rates where you're showing those. That might be a sell to right there. That might be a sell to the ham radio community. I know I personally use WhisperNet, right? You quickly check it, you say, show me the bands and color coded. Okay, here are the propagation conditions, so there's an opening into Europe on this band, right? So if this kind of plot could be kind of turned into a map display like that, that's a direct reason that ham radio operators might care about why they should set one of these stations up, right? And take the time to do the project, because it helps show them the propagation conditions and possibly the openings for contesting and other things, right? So that might be a way to help sell the overall value of one of hopefully many bullet points for how to sell the personal space weather station, and why we can do things like this, and you directly benefit by then getting an edge on everybody else and knowing where the openings might occur, right? So
yeah, I mean, that's exactly the reason why over the horizon radars send these signals, these sweeps in the first place. They want to sound the channel. They want to figure out what frequencies to use. So yeah. This is a direct data product that ham should be interested in, right? And the more the merrier that get this data. Let me show you an example of an animation. How much time do I have, Nate? I mean, when do we need to wrap this up?
Well, I can stay here for another hour, but
I have maybe 20 more minutes of stuff.
That sounds good. I mean, nominally this is an hour, but it's really however long people want to stick around and find it useful.
Oh. I have an example of here. This is an example animation of, can everyone see the video?
Yes. Yes.
This is an example of animation of these oblique inograms as a function of time. And there is a wealth of information here. You can see C-scatter, you can see multi-hops, you can see E-region propagation, you can see meteors, sporadic E, gravity waves. All these periodic oscillations are sporadic E, or gravity waves, are traveling ionospheric disturbances that show up in these inograms. So if we had a multi-static network, we could probably figure out what's the phase propagation of these TIDs, these traveling ionospheric disturbances. So there's a lot of useful information in these.
Yep.
That
The broadband version of what we're doing with the AM Doppler project
Yeah.
at Dartmouth, Juha.
yeah. How's that project, by the way, going? Are you still
It's going
using
quite well. We've got 6 receivers out and we're having a student analyze the data.
Nice.
Thanks for helping get that started.
Yeah, no problem. Here's an example of, this is when I started in 2011. I'm here in Sodankylä, northern Finland, listening to Cyprus, an OTH radar in the Mediterranean. This one was pretty nice, I think. You have a time of day variation. This time, the propagation distance is about 4,000 kilometers, and you can see, ground and sea scatter, E-region echoes. The time step is 5 minutes in these soundings, by the way. So you can definitely see where you have an opening, and during the daytime, absorption kind of kills frequencies below 10 megahertz, and above 10 would be nice. And you even get an SNR, so you can see where the signal is strongest, where the propagation is best.
You mentioned before that you just didn't have enough data to do the auto scaling.
Yeah.
So I guess 2 questions. One, I've got at least a couple 100,000, close to about 2 million manually scaled ionograms from digisones and caddies, mostly at high latitudes. But if you want them, I can make arrangements to get you some of that data if you want. But the second thing is, it's just something I haven't had the time to put a neural network together for, nor do I really have the skills, to be honest.
Well, we have some students who are, I guess all of you who are working at universities only have students who are interested in neural networks right now. So that's something that we can get students interested in. So yeah, let's talk about that.
The second thing was, particularly for the oblique, have you considered just creating just artificial or simulated data sets using, say, a decent ray tracer and an ionospheric model, just to get you some training data?
I have considered that, but I haven't done it. But I do know that for the PINS challenge, they did that because I looked at the ionograms, and after a minute of looking at them, I deduced that, okay, somebody has simulated these. And they were pretty well simulated, actually. I don't know who did those simulations, but they were really, really well made.
Yeah, they're quite clean, to be honest.
But they were too cartoon-like.
Yeah.
They didn't have any of the iffy issues that you have with real ionograms.
No patches, no TIDs, no. Yeah.
No light spreading. And
yeah. Anyway, sorry, but maybe this is an offline conversation at some point, but yeah. Cool.
All right, last topic. So in addition to these passive receivers, I've been working on for quite many years now on an HF radar, a software-defined continuous coded or coded continuous wave HF radar. And this spring, I had a master's thesis student, Marcus Floor, who did great work. Together, we made a new version of this code, which now functions as an inoson. It's a software only, it's a Python only implementation of an inoson. And it uses pseudo-random coded continuous wave transmissions. So it's kind of a spread spectrum signal. another example of a telecommunications or another example of a radio system that uses these kind of long coded signals is GPS or CDMA. So I'm using this type of technique for HF. And the reason why I'm using this technique for HF is because if you're using very long pseudorandom sequences that are continuous, you can use low peak power. A pseudorandom code will be orthogonal to everything but the same pseudorandom signal. So it will be tolerant to interference from other users of the band. You could even have multiple radars of the same type on the same frequency. As long as they all transmit a different pseudorandom code, they can all coexist and you can decode all of them. With some reservations, of course. This software can be used as a single frequency range Doppler sounder. So you get range and Doppler. You get power as a function of range and Doppler. But you can also step in frequency and you can use it as an inosond. And this is what Marcus did for his master's thesis project. You don't need a lot of power. I'm just using 400 milliwatts of power fed into a T2FD. So the effective radiated power is probably a couple of milliwatts on some frequencies. This system can be used because it uses long pseudorandom coded signals. Range aliasing or Doppler aliasing is not an issue. So you can use this for not only for vertical sounding, but also for oblique sounding of very long paths. You don't end up with range aliasing. If you have a long enough code, you can do round the world trip, you can do lunar soundings, you can do multiple times around the world soundings. Many interesting things could be done. The software, again, in my opinion, there's only one nice software-defined radio for HF, and that's the N210. I'm going to definitely look at the Kiwi SDR. That might be an interesting option, and Tangerine SDR is for sure going to be interesting. But I didn't know better, so I implemented this for the USRP with a GPS DO. I only rely on the UHD drivers, for the Universal Hardware Driver. It's not very universal because it only supports EDIS research devices, but it's a very simple API. I think it wouldn't take much to translate this code for other radios. I mean, the code itself is not many hundred lines of Python code. A previous version of this radar is already used by Dave Heisel from Cornell. He's got a network of single frequency sounders in Peru, and he's using them to characterize the waves in the bottom side of the equatorial ionosphere, which he then uses to predict equatorial spread out, to predict the how the equatorial plasma bubbles are formed. So he's using a ray tracing inversion scheme where he uses these multiple links to figure out what is the three-dimensional structure of the ionosphere on the bottom side. And there's a few papers out on that topic if you're interested in it. This is kind of the next generation of this radar that I developed for Dave. And I'm hoping that many people will adopt it. I've already talked to Devin Huigebart at Saskatoon. We've already actually tested it at the University of Saskatoon, and it worked. The code is, again, open source. You can download it on GitHub. There's a thesis. There's a thesis. Let's see if I can download this thesis. Oh, okay, now I lost it. I think I crashed my. Yeah, well, here's the thesis. The thesis is online. If you're interested in details about how this was constructed, the title of this thesis is Design and Implementation of a Software-Defined Inosond. All of you are very technically savvy and engineer-minded people, so this will probably not be, this is somewhere in the boundary between engineering and space physics. So you probably need to fill in a lot of dots in between, but I'm pretty sure that all of you are able to do that. But it has some discussion about ionospheric plasma and radio propagation and Appleton-Hartree, and then it has some discussion about radar signal processing and then it discusses the implementation of the ionosonde. Here's a block diagram, for example, for the ionosonde. It's very simple. It's very, very simple. Just some mini circuits components that are off the shelf, a USRP and GPS DO. This is all.
Where can we find this?
There's a link on the slide, and some block diagrams, flow diagrams for what the code does and what frequencies we got a license for. We went the right way. We applied for a license and got it, and we didn't get all the frequencies that we wanted, of course. Some testing and we even verified that we meet the license requirements, that we are radiating less than 1% outside of the license band. So a lot of details here. There's even some pictures of the installation. Here's the picture of the antenna. It's a T2FD folded dipole. Very simple, off the shelf. You can get this from ham radio outlet. Receiver antenna. The only exotic thing about this is the location. This is at 78 latitude. This is on the so far up north that it's on the northern edge of Greenland. And there's
so far north you have to look south to see the northern lights, right? Yes,
exactly. And there's some traces. This is an example ionogram using this ionosonde. It's pretty sparse because we only got a license for a handful of frequencies, unfortunately. Maybe in the future we'll get some more frequencies if we beg harder. But you can still do useful stuff with sparse ionograms as well. I mean, I can still eyeball where the O-mode cutoff approximately is. And I can tell that there's an E region, and I can even approximate where the E region cutoff is. And for sure, I can say where the E region height is. So, and you can track sporadic E location. The ionosphere is also very strange at Svalbard. We're in the polar cap, so we mostly get polar cap patches and sporadic E. I'm sure that David is also very familiar with the weird polar cap ionosphere. Anyway, and one of the interesting things about this ionosonde is that every measurement is a measurement of range Doppler. So here's Doppler shift, and this is range. This is for the sporadic E layer, and this is for, there must be an example for another example. Well, I have it in the slides. Okay, so the link for this thesis is available in this link here. I think it was Scotty who asked us. This is where you can find it. This is being recorded, so I guess you can find it. But if you have problems finding it, just send me an email and I'll send it to you. I can also share it with Nate, and Nate can. If you have some.
If you can send me a PDF, I can post the PDF along with the recording.
Yeah. Okay.
Or you can cut that out and paste it in the chat room, chat link.
Yeah, that's the other good thing to do.
Then we can all grab it.
I don't have the chat window here.
Looks
I'll do that later. I'll do that last. I'll try to remember to do that last. Okay, so here's what
we've got it up already. Thanks.
Yeah, here's a kind of like a vision of what this ionosonde could look like. I mean, you just have a small computer and a couple of antennas. I mean, I even played with the idea of having a tunable magnetic loop antenna for transmit, so you could fit this ionosonde in a suitcase. And I built a prototype with a summer student, but we didn't really make it production quality, so that didn't survive. I mean, we got the SWR down to a pretty good level, but we didn't end up with something that we could just keep running. That would have required a little bit more work. Here's an example ionogram. I already showed that. Each frequency, what this radar does is it stays on each frequency for some time. I mean, that's configurable. In this case, it stays on one frequency for 4 seconds. and you get complex, after you've done the deconvolution of the coded pseudorandom code, you get echo amplitude, complex amplitude as a function of range and time. And then if you Fourier transform this along time, you can get the Doppler spectrum for each range. So the bright spot at 0 frequency Doppler shift and 0 range, that's the transmitter, which is right next to the receiver. And then you have a distribution of echo power coming from 200 kilometers, which is the F region. One of these is going to be the O mode and one is the X mode. And then you have, because this is the polar cap ionosphere, it's pretty patchy. So that's not coronavirus related, I hope. Yeah, so one of the nice things about this is that it characterizes your channel in terms of range and Doppler.
Is it operating now?
What?
Is it operating now?
It's operating now.
So I can listen to it.
You could listen to it. I can give you the code even if you want to. I can even give you the software to listen to it if you want.
Oh, that'd be great. If you tell me where it is, I can download it myself.
This is the real-time plot of the ionizon. So you can see that there was some sporadic E a little while ago, but then it went away. And there was sporadic E earlier. There was 1, 2, 3, 4 hop sporadic E. Sporadic E is very common occurrence. And then there was some very patchy plasma. So there was some F region plasma convecting across Svalbard. This is the, this last plot is time. So this is day, month, no, month, day, year. No, what? What is 0, 2? Oh, that's the, okay, day.
02 is the hour, so it's a month,
Day, hour.
day, and then hour, I think.
Yeah.
Or it's or no, it might be.
This is
It's
48
hour.
hours. This is 48 hours of data. So the last number is
Yeah.
hour.
Yeah.
And then you've got the day, which is today is the 2nd, and then you have the month.
Yeah.
The format is not the best, but you know, Matplotlib gave me that, and I didn't go through the trouble of making it more human readable. I'll get to that. But this is time on the x-axis, and this is frequency on the y-axis, and you can see the cutoff frequency as a function of time. And it's a little bit jagged because, again, we only got 30 frequencies, but it's still useful. And if you want to listen to this, you can get the code for the ionizon. If you have a USRP N200 with a GPS DO, you can just run the RX UHD.py. This will record the signal using GPS timing, and then you can do an analyze ionogram.
If that records signal, it suggests that I'm receiving a certain HF signals, right?
Excuse me?
If that records signals like the program that you suggested,
Yeah.
that suggests I'm receiving some oblique signals.
Okay, very good.
No, I'm asking you.
Oh,
let me put it this way, okay? If I ping, like I have installed USD and the N200.
Yeah.
And I ping and I receive data.
You ping,
Yeah.
like as in the ping command, or?
Yeah, I ping the device, okay?
Yeah.
I could sort
like
it.
Ping 192, 168.
Yes.
And 2 or something like that.
Yeah. So, and I receive data, okay?
You'll receive the ping response, which is telling you that, okay, you have connected to the device.
Okay.
Yeah.
Okay.
There's also a command called UHD find devices, which will look for devices, and I don't have any devices connected right now.
Juha, I'm wondering, how complex code are you running in the EDIS research receiver? the USRP. Are you just down converting?
Yep, it's just doing a digital down conversion and digital up conversion.
Yeah, the reason I asked that specifically is that, you know, they were talking about Kiwi, but there's also the SDR Play SDRs that are quite inexpensive and give you very good bandwidth, 2 megahertz 2-channel or 10 megahertz single channel.
What was
I
that
wonder if
device
those
called?
could be used in this.
What was that device called? It was
SDR Play is the company, and their RSP 1A is the low end one, and there's an RSP Duo or Pro or whatever they're calling it, the high end version. It's between like $100 and $250 instead of the USRPs, which are like $1,500 still.
yeah.
And do much the same thing, except not as programmable.
Yeah, I mean, it is possible to, I mean, I only use, for this application, I only use 100 kilohertz of bandwidth. I mean,
Right.
because of the ionospheric spreading, I don't really want to send more than that.
Yep.
So, but to do the ionogram, I just hop from one frequency to another, just like a Digison would do.
Right.
So it doesn't require a lot of instantaneous bandwidth, but it does require precise microsecond accurate timing of your tuning.
Right. Well, one of the higher end, some of the higher end versions of that have an external frequency input that you can lock to and such. I've been starting to work with those. And of course, the RTL SDRs, as you've done yourself, we lock those to GPS. Did we lose Juha?
Did we?
Juha seems to have frozen.
Yeah. Yeah, I think we did lose Juha. Well, we'll give him a couple minutes.
Give him a moment to come back.
Yeah, I guess while we're waiting, we can chat if anyone wants to discuss anything.
To throw out one detail about the SDRs, because we played with many different kinds at VT over the years. The basic model is the raw IQ transport. So earlier when we were talking about that, Scotty, for your information, the protocol that Edis uses is a flavor or subset of Vita 49, which is a common radio over Ethernet standard. There's a new one that's coming out from IEEE that's an open standard, which is nice. That's another newer radio over Ethernet. But that's a common framework for just digitizing and transporting raw IQ over whatever the interface is, whether it's Ethernet or USB. There's an Osmocom kind of library for GNU Radio that has the drivers for many, many, many common like different kinds of SDRs you might want to use with GNU Radio.
Yeah, what I noticed about Vita 49, it seems to be pretty much open format. I mean, they have particular headers like a timestamp and things like that they define, but the actual data field is open.
Yep,
so,
that's the exact problem with Vita 49 is that one company's Vita 49 is not necessarily compliant with another company's same thing, but they also call Vita 49. That's why I say it's an Edis flavor of Vita 49.
Yeah, so I think what we're planning to do is define in our protocol document different flavors of Vita 49 that we're going to implement, and then we get to pick. I mean, we don't get to pick, but obviously you can't implement all of them. But if we pick some standard ones and we pick ones that other people do, then we can implement those, and you can request different formats, and you can the format that you need.
Yep. And then one other thing to throw out is, I'm not sure if everybody's heard of this, is something called RF NOC, or RF Network on a Chip. And there's a companion project, or a similar but different project called OpenCPI that's all about like what GNU Radio did for general purpose processing in terms of making it easier for the non-experts to do software radio. That's what RF NOC and OpenCPI are trying to bring to FPGA and GPU development. So the idea is about moving stuff over to the FPGA to minimize the streaming RF knock might be a good candidate for something like that, but again, that's somewhat targeted towards Edis products, but it's not beholden to them. OpenCPI is a little bit more open in terms of working on various different FPGAs and different types of implementations. So just throwing that out in 2 cents. It looks like we've got Juha back though. So
Yeah, am I back? Can you hear me?
yep,
You're back.
Yeah, my Zoom crashed. It just disappeared. So, but I'm back. I'm almost done. So maybe I just show my few more slides and then we can have some more discussion. This has been a nice discussion. So share. Oh, can you give me the permission?
Oh, sorry. Yes. Go ahead. You should be good now.
Okay. It's visible still? Like the slides
Yes.
are visible? Okay. So I don't know where I left off, but I guess I went through most of this, and future work. I was trying to think about what should be done next. I mean, obviously there's some more software work that needs to be done. I'm really looking forward to this Tangerine SDR or any of the other SDRs that are coming online. I've only used the USRPs mainly because they were pretty much the first consumer grade devices out there, and they were really nice. They supported open source. And by the way, Edis research, Matt Edis always says that they're not research grade, they're communications grade. So a lot of times people actually will say that these devices are not suitable for research because they're so inexpensive. So I think it's not, the cost is just one factor. I mean, I think you can do research independent of cost. I don't think high costs equals good research. So if you can make a low cost SDR like Tangerine SDR, then your research becomes, instead of having one Inosond, you can have 10 or 100 Inosons, and you can build a network and you can look at the mesoscale dynamics of the ionosphere instead of looking at the ionosphere at a handful of places. So yeah, new hardware is interesting. I think also it would be interesting to see if this software would run on inexpensive, small computers, low power computers like Raspberry Pi. Alex Chartier, he said, the first thing he asked me when I mentioned the Inoson, he said, "Oh, I can run this on the Raspberry Pi." And I'd like, no, I've never tried it, but that's a really good idea. NVIDIA has this really interesting platform, Jetson Nano, which has a GPU on it. It's like a Raspberry Pi with a GPU. I just received one the other day, and I'm going to play with it to see if I can offload some of the processing on the GPU. If we can make the software available on a Raspberry Pi or some some small microcomputer, then we can publicly distribute an SD card which has all the software pre-installed and it'll just work without any installation. I think that would be a nice feature, so that anyone, even if they're not technically savvy, they can string an antenna on a tree and plug in an SD card image and get rolling. I mean, and do science, contribute to doing science with the personal space weather station. I'm pretty sure you already have all of these ideas, but these were what I thought about. I think the open source Inosond, I think one of the applications that I have in mind is this DASI type. DASI is a distributed array of small instruments, and I think that's where the funding for the Tangerine SDR is coming from. National Academy of Sciences decadal survey indicated that it would be a really good idea to go from these gold-plated instruments that are we only have a few of, expand our observing capability to dense networks of instruments. And I think this HF beacon network, this coded continuous wave beacon network could be such a network. I mean, we could have this HamSCI community we could run our own Inosond network with some people and some people having a site for a transmitter that anyone can receive. It would not only provide ionograms, vertical ionograms, oblique ionograms, but it would also, this kind of a network could also provide location services and timing services. You could distribute timing through such a network. If all the transmitters were GPS locked, then all the receivers could derive their timing information from the network. And one thing that I want to throw out there, the GNU Radio community has a GNU Radio conference every year. And I've been to a few of those conferences, and one of the best parts of this conference is the GNU Radio Hackathon. And maybe we should have a HamSCI hackathon where we pick a project and we try to work on making progress on that project. I would certainly be very much interested in participating in such an endeavor. Anyway, that's all I wanted to say. I'm sorry it was 1.5 hours, but there were a lot of discussions. So I think it was okay that I went half an hour over time.
Time well
So, any
spent.
more questions,
Thank
any
you.
more comments, discussion?
I think that was a really great presentation. Thank you. And I would certainly be open to the hackathon idea. Hopefully we'll have an in-person HamSCI workshop next year. Maybe we can integrate it into that. I think that's a great idea.
I would throw out or add on to the hackathon idea that they also do Hackfests outside of the conference for particular topics. So one hot topic that they presented on last year and did a second follow-up on was phased array work with radio observatories, specifically the Hack Creek Radio Observatory. And we might be able to encourage them, if there's a particular area of signal processing or GNU Radio develop or something like that that's maybe too challenging for us or we don't want to take it on, we might be able to partner with the GNU Radio community and encourage them to come to a kind of off-site Hackfest somewhere where we sit down and get sort of the people that know the ins and outs to handle the things that we can't handle on our own or don't want to handle on our own. That might be another good way to get some involvement there. There's a strong partnership with the amateur radio community and GNU Radio, so I think they would definitely be open to that.
That would be really good.
Yeah, and I don't know, the GNU Radio conference was going to be in Charlotte right after the TAPR DCC conference, and I believe this is the case that I know TAPR DCC conference is going to be virtual, and so is GNU Radio conference this year. But next year we're going to be back in Charlotte because part of the deal of canceling this year was to move it to next year. I believe it's going to be the same deal with DCC and GNU Radio conference next September in 2021. Because they're going to be back to back at the same venue in Charlotte, North Carolina. So that's some good synergy between the groups.
Yeah, that would be fantastic.
I know it's interesting that you go to the DCC and it's a bunch of amateur radio operators mostly, and they're all old. And then it transitions to the GNU Radio conference, and all the old guys leave, and it's all the young people. It's very markedly different audience.
Are there any other questions for Juha?
Just Scotty, is there any divide in the skill set either? I mean, young people know how to do software, and the old people know how to do RF engineering.
It is exactly like that, and the young people are. The GNU Radio conference is pretty much a USRP fest. Okay, so all the hardware was just canned USRPs. Everybody uses those, and then all of the innovation was in the different software things that they do with them.
Yeah.
And GNU at DCC, it's a lot more. I wouldn't say it's a hardware centric, but it's a lot more varied in types of hardware they use, like
Wrapping up.
Raspberry Pis with RTL dongle.
Oh, right.
What kind of hardware they're using.
Oh, about an hour and a half.
So it is, yes, the hardware is very homogeneous for GNU Radio and less so for the DCC. And the topics too on the DCC are, I think, more wide-ranging topics, whereas at GNU Radio it's very much radio-centric and what you can do with the USRP and GNU Radio.
They do have, I think at the GNU Radio conference you do see a wide range of different hardware nowadays too. It's not just USRP.
I haven't been in about 5 years, so and I've heard it has changed. So I was looking forward to this year in person, but I guess we'll do this year virtual, and
Yeah.
It'll be good.
And there's a lot of cool things at the GNU Radio conference too. I mean, one year, the first time I went there, I figured out that okay, the microphone has an FM radio channel. So then it became a competition for all of the attendees to hack the microphone.
No orange envelope.
Yeah.
And then I went to Las Vegas, and that was again what people were doing. So I think there's a lot of fun stuff happening there.
And I think in terms of applications, it was much broader at GNU Radio because it was like whatever your imagination could come up with. And so you sit back and you listen and you go, wow, I didn't think of that. And here's a guy in the front who wrote some software to do some particular project. Whereas on the DCC, we're just all diehard hams, and it's like, it's doing the same thing that you did with your old radio, and now you're doing it with new hardware. So it is a lot different.
One other thing to keep in mind too, it's not always obvious at GNU Radio, is there's a lot of government kind of involvement with the software radio framework, specifically GNU Radio and a whole bunch of others. So the networking opportunities, particularly when it comes to funding, are really good at GNU Radio. It kind of feels like this fun, open conference and all of that, but there are some, DARPA representatives there and other DoD and intelligence community representatives, and this kind of work is directly relevant to them. We should consider that as potential funding sources. And they're actually even getting better about open sourcing software and letting software be open source, even though, Air Force Research Lab or something like that paid for it for maybe an IC application. So all good stuff.
If we have a couple minutes, I've got something I'd like to show the group and get an opinion about. If I could bend your ear for 5 minutes, something of a sort of a practical nature. Some of the folks in the Case West group might have heard me talking that because I've found the red pitaya clock to be so unstable, I'm wanting to, instead of using the red pitaya to simulate the data engine, I'm wanting to use my Flex radio. And I'm finding some challenges. I finally got it to where it will spit out what appears to be, best I can tell from the documentation, IQ data. However, I'm having a little bit of trouble understanding what the IQ data is, and because this is not documented anywhere. Could I share my screen here?
Go ahead, Bill.
Okay. Let me show you what it looks like.
Before you keep going, Bill, I just want to check. Juha, I know it's quite late in Norway, so if you want to go, I just want to take a moment to thank you for coming and giving this presentation. I really appreciated it, and I think everyone else did here as well.
Yeah, no problem. I mean, I should probably start participating in these meetings. You have them regularly?
Yeah, so we have them every other Thursday, except next week we're going to start again. We're going to have one next Thursday, and then it goes back to the bi-weekly cycle. The format has been a little bit, sometimes it's just general discussion, like we probably won't have any one particular speaker next week. We'll probably just say, people will just give updates on what they're doing. Sometimes we have a specific speaker like you were today, and we had a particular, presentation. So it changes. But what I'll do, if you join that HamSCI listserv, go to hamsci.org and get involved, or I can help add you. I usually send out a couple days ahead of time what the plan is, whether we're just having a general discussion or a specific speaker or something like that.
Yeah, I think I'm already on the HamSCI mailing list. I just it goes to I filter my email, and I haven't looked in that mailbox or that folder often enough.
Yes. Well, yes, please feel free to join us. We'd like to have you back more often. And we will keep in touch.
Yeah, I'll listen in. This is so interesting that I don't really need to go yet. I mean, it's
great.
Not even 11 o'clock yet.
Yeah, thank you for your presentation. It was very informative.
Very good presentation, Juha. Thank you.
Thank you,
Thank
Juha.
you.
We really enjoyed it.
Yep.
Well, yeah.
Thanks very much. It was great.
I guess
Yeah, I
we'll
see.
say good morning to you.
Yeah, I can see Dana Whitlow. Is that Dana Whitlow there?
I think it is.
Yeah. Hey, Dana. Yeah, maybe he's not there. Yeah, yeah. Just keep going on with the discussion, and you're welcome. And anytime if anyone wants more information, I'll be more than happy to give. And I've learned a lot during this telecon from you guys. So there's a lot of stuff that I need to follow up now on.
Thank you. So yeah, why don't we keep going? We'll wrap up within 20 minutes, so by 5 p.m. Eastern. And until then, go ahead, Bill.
All right. So this is a buffer of UDP data coming from the Flex radio, and it is in VITA 449 format. And the data, the actual data that is supposed to represent signal data starts right in here somewhere, but I'm all right. Now the Flex radio uses a 16-bit A to D converter running at 246 megahertz, something like that. But I don't think they're just putting out the data that I'm looking at does not look like samples coming directly off the A to D converter. It looks like it's some weird things. What I'm speculating it might be right now is it might be 24-bit floating point little endian, where you have to take each 16-bit pair of bytes and then rotate them 8 bits, but I'm not sure. So okay, this is the radio when you have the grid grounded. See, so they're supposed to be IQ signals. So you've got some zeros in here. This column is always zeros. So, but now you put a strong signal into the rig. That's why I'm thinking this might be here over here exponent.
Bill, what I'm seeing is the screen of your Flex radio. Am I supposed to be seeing data?
You're supposed to be seeing data.
I see the screen.
Yeah, we see the Flex control panel.
I don't.
Sorry, let me try and do this again. I picked.
Oh, you picked the wrong window.
Now what do you see?
Okay.
Now it looks like I got some hexadecimal dumps.
That's what I'm looking at. Yeah.
Okay.
Okay, it was seen your desktop.
Yes, that is correct. So what you're looking at here is supposed to be IQ data from the Flex. So the data starts over in here where there'll be zeros and then some hex numbers, zeros, and then, but these numbers always begin with a pair of zeros. And then once you start putting signals into the rig, you start getting what looks like some small exponents. That's why I'm thinking this might be, this being one of your, for example, this is either an I or a Q.
Yeah.
If it's little in, this would really be Charlie 000, and then this number would be Charlie 62 Echo.
Okay, Bill,
Does anybody recognize this at all?
You want to get the Unix utility called ghex, G-H-E-X, and install that, and it will let you point to a file like this, and it'll show you the decode for almost every possible number representation, little Indian, big Indian, floating, fixed. It'll show you all of those in different windows.
Okay, so noted, Tom. But the thing is this familiar to anybody at all? Has anybody ever seen a data format like this? I guess not.
It looks like, I'm going to say it looks like a two's complement binary.
So typically, these IQ streams, I don't have direct experience with the Flex systems, but we worked with them a good bit. Not directly to pull IQ off, but we've looked into that. And I know one thing that you'll definitely have to, that's a limiting factor with them, is you are correct in that it's not direct from the ADC. They instantiate the slice receivers on the FPGA, which do the digital down conversion and limit you to a maximum of 250 kilohertz. So whatever the stream is, but I think you can instantiate up to, like, depending upon the model, something like up to 8 independent Flex or slice receivers, and then pull the streams off of each. It's probably some kind of interleaved complex data type, meaning that a very common one for linear radio, for example, is complex 16, I think is the right way of saying it, where it's a 16-bit I and then a 16-bit Q, right? So this could be some other data type, which is not necessarily directly mapped to the ADC bit depth, right? So after the down conversion and the coding gains and all of that, it could be a much higher resolution than whatever the bit depth of the ADC is. But you're not ever gonna get like a full 240 megahertz if that's the clock rate of the ADC. USERPs do something similar, where the clock rate's always running higher than whatever the quote sample rate is that you're getting out of the USERP.
Right, that's clear. This is coming off of a single pan adapter, which is already been down sampled and stuff, and you've got a known center frequency. So it's IQ data around a known center frequency, and I know what the sample rate is. In this case, it's 48 kilosamples per second.
Bill, is this off a pan adapter display, or is this off a virtual radio display?
Stand by. With a Flex radio, you have the choice of selecting if you want it to give you the wave data or the IQ data. In this case, I have selected data from a single pan adapter, and I've requested IQ data.
Okay, so you've requested because of what I remember is the way the Flex works, and on a pan adapter display, you get like 1,000 IQ samples raw directly from the ADC if you pick that format. But if you said IQ data, right? So as opposed to what was just said before, I think Zach said this, that you get a downshifted and filtered version, but the pan adapter, I believe, is raw data, because that just gets the FFT gets in the PC, and then that gets displayed on the screen.
Well, I mean, it's supposed to be IQ data, the same stuff we're planning to get out of the data engine. Well,
it could be IQ data, but it depends on how much processing you've done on it.
Depends on how much processing Flex has done on it. Yeah,
right,
and
it's
clearly been processed in some way. What I'm trying to get at is okay, I'm wanting to take this and then spit it out in the same format as if it was coming out of a Tangerine data engine. So I've clearly got to know what it is. But you know, I can see. Here's the thing. I'm not sure if I'm, you know, say I use G-Hex like Tom was talking about. Okay, I can look at it in a half a dozen different formats, but I'm not sure I'm going to know which format is the one that I want. I mean, I've got the programming skills to do the rotation, and I could even reverse the bits if I need to, if I know what I'm supposed to do.
So I suggest that you write an email to Steve Hicks. Do you know Steve Hicks? And
I don't.
I can send you his email. He's the VP of Engineering at Flex, and I'm sure.
Oh yeah. Okay. Yeah. I think I did have a conversation with him on the community thing. He was not helpful at all, but I can try it again.
Well, okay. Or I can ask him. I mean, I've been pretty friendly with him and talked with him about a lot of things. So basically, what you want is raw IQ data coming out of the radio. How do we do that?
Well, I'm doing it. I want to know how to interpret it.
What's the format of the data? Okay.
Where's the ICD that defines all of this?
Say that again?
What the ICD that specifically defines all these formats, so that you can develop it. They should have something. That's exactly why we kind of dropped the Flex and went back to usurps. Is the documentation for the raw IQ interfaces were not very well defined, and because the ICDs did not exist, and it was all this swapping emails, and I think it's this, but it might be this. We just kind of ignored it and went on with something else.
Yeah, I get maybe I'm having the idea that they maybe they think this as being somewhat proprietary and really don't want you to know what it is.
Maybe, but the entire reason we engaged was to try to write a GNU radio driver as like a replacement for UHD that would drop in and be a Flex radio interface. So in a certain respect, I don't understand why they would want to keep something like that totally proprietary, because it limits, right? They could open up the market to a whole new class of users, maybe outside of ham radio, if they
I would think they'd want you to be able to do that.
Yeah, I would think so. I mean, here's the thing: is if you can't make use of the data, it defeats the purpose of even having the option on the radio to request it to output it.
Exactly.
That was their major marketing platform, was that this was going to be open source. Because I had a Flex 3000 before I got to 6500. Of course, they dumped that when they said they would be supporting it for life. Question for Bill: did you ever figure out on your Flex the problem with the virtual comm channel going away?
There's not a simple answer to that. The problem comes and goes.
Because I think I've seen it on mine as well, and I never figured it out.
Where it's like you start getting a whole bunch of jitter in the timing of
and then it just
the driver, and sometimes you'll get a Windows update which changes the characteristics of it. So Flex is quite logical in their saying that there's nothing we can do about this. It's related to something going on at the driver level on the Windows system. But okay, a couple of things. To a note to Scotty, the Flex Radio community that normally would discuss all this stuff went down hard at the end of the day at the end of June, because the company that provides that soft website kicked Flex off, and they're right now trying to find another provider and then take and convert all of the historical discussions and everything. So right now you can't really discuss anything with anybody about this. Now if you've got access to Steve by email, he might be able to tell us something. And all the simple things I've done. I know how to talk to the radio with TCP/IP, to turn a slice on and to tell it to start outputting. You've got your choice of DAX data, which is WAV file format, versus DAX IQ data, which is supposed to be IQ. And I've got the VITA 49 standard, and I've looked at it bit by bit. But the VITA 49 standard doesn't specify the format of the IQ data itself.
Right.
That is vendor specific. So I need somebody to tell me down. I want to know the bit layout. I don't want general discussions about the interface and all that. There's plenty of that online. I need to know the bit layout.
So what you want is in the VITA 49 packet, what's the layout of the IQ data?
In the Flex, the layout of the IQ data is not specified by VITA format. That is I was going to say proprietary, but it's.
I'm trying to condense this down to something I can ask Steve that will be a very concise question and a concise answer, because if it's going to take too much time for him to go look it up, then I probably won't get an answer.
The terminology I've used for this kind of questions with other systems is what is the data type and the endianness of the IQ format, right? Is it complex 32? Yeah, is it complex 32 or complex 16 or real data, right? And then after that, what is the endianness? Is it, least significant or most significant bit first?
Yeah, I'm pretty sure it's complex, because if it's IQ, it's by nature it's complex.
Right.
Oh,
usually it is. My guess, just looking at all those zeros and that kind of the weaker, like no signal example on the left, is it looks like complex 32. right? It's almost like the higher order bits are not being exercised. That's why you're seeing all the zeros. And then you've got some noise that's exercising the bit or the ADC, and then you've got a repeat of that with the next kind of pair of numbers there. So that would be 32 bits per independent sample, where it's 64 bits total for one quote complex 32 sample, right? Where
Right.
32 bits die, 32
I'm
bits.
quite
die.
sure.
That's what
I'm
it looks
quite
like to me.
sure each IQ pair adds up to a total of 64 bits, and
Right.
there's 30 bits per I and 32 bits for Q. But then once you get down into that, is it 32-bit floating point with the most significant bit on the right, or what? And where is it signed? Is it the sign bit there? I mean, this thing right here, this 80, for example, I'm guessing that's a negative number, because if you rotate this and put this on the left, that would make that 8 would, in the highest order position using IEEE format, that would make that a negative number.
Yep.
But how,
Typically, when you say something like complex 32, what you're actually saying is a float 32I and a float 32Q
Yes.
under the IEEE definition for that. So that would be my guess. And then the next trick is just flip the endianness to see and compare the spectrum to see what makes sense and what doesn't.
A float 32 is like 6 bits of exponent and 20,
Yeah, the
like that, right?
and all that kind of stuff. Yeah.
that is, let me see. Are you seeing my screen here?
Bill, I'm gonna
standard-
sign. I need to go for now, but I'll leave the channel open so you guys can keep talking. Okay.
Okay.
Okay. Thanks, everyone. Have a great day.
Thanks,
Thanks,
Nathan.
Nathaniel.
You're
Yeah.
welcome.